All right, well, let's go ahead and start with thermo. It is a subject that you need to understand that these laws that we're going to be talking about are laws that are based on observations. Okay, things that we absolutely are certain are true, but they were laws that have sort of been formulated throughout time. And but basically what we're saying is you cannot destroy or create energy. Okay, mass is conserved. So that's what this is about. Okay, so the first law, the universe, and we mean out to the outermost star. We have the system, which in my world is Don Blake. Okay, this is my system, and everything out there is the rest of the world. And we base things, folks, on whether the system gains or loses energy. Okay, we're always concerned about the system. Okay, and it's a little confusing because sometimes the signs for work and heat don't make sense. You need to think of it as money in my wallet. Okay, this is all about me. If I take my wallet out and I give Rafe $5, should you show that as a +5 for Don or a -5? -5. I'm $5 short, right? He's +5, I'm -5. That's how things work. Okay, pluses and minuses all have to add up to equal 0. The point is that if I end up doing work or giving heat to somebody, then that sign is a negative. Okay, it shows that I gave something up. I might have done work on, and we need this kind of understanding. This is like when you put gasoline in your car. Okay, it does work. But as it does work, do you gain gasoline? No, your gas tank empties. Okay, so once again, that is a negative flow of resources. Okay, so we're going to be talking about surroundings and the system, and it's important. It's important, folks. There's a lot of equations. Okay, just so you know, I will give you 0 equations. Okay, you're going to need to know these equations. I will not give you anything on the exam. Okay, what I will give you are constants and things like that. Okay, so if you need to know, that E equals mc squared, then I'm not going to put that on these. You don't need to know that, but that's one everybody knows. Okay, I'm not going to give you PV equals nRT. I expect you to know that. I'm not going to give you the area of a circle or the area of a square. Okay. Those are things you need to know, all right? Constants are less important. So when I took thermo, so this is like basic thermo, although this book is not quite so basic. There are 3 laws of thermodynamics, and the way I was taught was that the first law of thermodynamics says you cannot win, you can only break even. So the best you can do when it comes to getting energy out, the maximum amount of energy you can get out is equal to the amount that you put in. Okay, so that means you can't win, you can only break even. Second law says you can only break even at absolute 0. And the third law says you can't get to absolute 0. Okay, that's just life. Okay, and those are the 3 laws of thermodynamics. Hopefully, in another 3 or 4 weeks, you'll be able to look at this and say, okay, now I understand what they mean by this, and now I see what they mean by this, and now I see what they mean by this. Okay, but those are the 3 laws, and sometimes there's 4 laws. One says, you have to deal with it. Okay, in other words, you have to play the game. All right, state functions. This is an important thing to understand. A state function does not care about how you got to a particular place. It just is happy you're at that place. So I look at you folks, okay? How many of you came from the dorms today? How many of you, raise your hand? Okay. So you didn't have to put a whole lot of work into getting here. Okay, maybe it was tough getting out of bed, but how many drove from at least 10 miles away today? Okay, how many drove from 20 miles? Okay, there's some people with their hands up. 20 miles is a lot longer than what you people who walked here had to do. But you know what? That person who drove 20 miles has to take my exam. There's going to be 100 points. And if they get 66 right, they get 66 right. I don't really care how far they had to come. Okay? The fact is that they are here in this room. You are a state function. I don't care whether you went to 6 schools before you got here or whether this is your first college. Okay? That's what a state function means. Doesn't completely blind to how you got here. All right? So that's an important thing for you to understand. So a state function, once again, is only on the current state of the system and independent of how it got there. These, pressure, volume, internal energy, entropy, and Gibbs free energy, we won't talk about this in this class for right now, are all state functions. Okay? So pressure, volume, internal energy, and entropy are all state functions. Mechanical work and heat, okay, are process quantities. They are not state functions. These are two things you need to know. Heat, mechanical heat and work, or mechanical work and heat are process quantities because their values depend on the specific transition between the two equilibrium states. We will be going over that later today, and you'll then all of a sudden go, oh, now this makes sense. So don't panic. And folks, this is all, I sent you an email. I sent 2 emails, I think. I sent one that, I think I sent 2 today. One that says the notes were posted. That was yesterday at about 3:30. And then another one shortly after, yeah, that said that this lecture, because there's a guy, this little black thing on my chest right here, there's a guy filming this. And these films are posted on YouTube or someplace. And so I sent you the link, not that you want to watch me again, but it is posted, okay? So make sure you're always checking your emails. Okay, I'm not sure why I said that. Okay. What's important for you, once again, I said that work is not a state function. So that means that the change in work is not necessarily equal to the final work minus the initial work. Now that's not the case for volume. Okay? If I've got 5 liters and I expand it to 10 liters, then its final minus initial, it'd be 10 minus 5 is delta V would be 5. Simple math, okay? If you got a state function, that's how it works. Work isn't like that, okay? Work, it says it's not equal to it. It can be equal to it, but it doesn't have to be equal to it. So this is more of a non-Don Blake-centric world. You have the system. Doesn't matter if it's a test tube, an engine, a school, okay? You can define the system however big you want, and then everything else is outside, okay? If this is UCI, then this is Irvine and Costa Micas and then blah, 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 okay? And we're talking about energy that is moving this way or this way. You are either gaining energy, losing energy, or you're out of the game. There are 3 different types of systems that we'll be looking at. There's the open system, okay? That's a system where, since it's not closed, if I were to boil this, okay, or heat this up, I could have water vapor coming out, okay? In this case, if I were to boil this or heat this up, this would have a change in pressure, okay? Because it would be warming this up, more water vapor up here, we put more pressure up here. So this is a closed system. An isolated system is one where there's no transfer of energy. Okay. If this one is a little bit similar to this. Okay, I bought this an hour ago. It's not super cold, but it is colder than it's going to be in an hour from now. Okay. So this is a closed system. It looks like this, but there's no insulation here. What do they call those things that you put like on a, you don't know what they put on a beer can because you're not old enough to drink beer, but like on a soda can. What do they call those little like foam things? What? Koozie. A koozie. Ever heard that word? Okay, it must be an East Coast word. Anyway, but But yeah, put some foam rubber or something around this thing and it would actually keep it colder longer. Put a wonderfully big insulator around it and it could stay cold for days. Okay, so this is going to get, you can have something happen in here, it's closed like my top is on, so this is a closed, this is now an open system. So this is picture number 1, picture number 2. Picture number 3, I'd have to wrap this in all kinds of stuff to keep it so that the energy would not, the heat wouldn't come in and warm up my drink. Those are sort of 3 different things. Now, we're going to be talking about work. Look at this first one. If I warm this up and start to boil water off of this, let's say this is glass. I boil water off of that. So it's getting hotter, but is the volume changing? Okay, you've got liquid, okay, and as you boil stuff off, steam comes out of here. Would you say that's a change in volume? Yes. I'm not saying that this glass vessel is changing in volume. I'm saying that the water molecules are jumping up and they're actually pushing out this way because they're hotter. In this case, they can't get out. Okay? You heat this up, you got that top on there, nothing gets out. And in this case, first of all, you can't heat it from the outside, and the top can't get off. Work, folks. Work is defined as the change in volume times the pressure. Pressure times the change in volume. So if you were given these 3 pictures, which one of the 3 could actually do some work? Which is the only one where the volume can change? This one. If you've got a closed system and it's really closed, you cannot do any work. Work is equal to 0. Okay? Now let me just, thermo, folks, this kind of thermo is not easy, okay? You can go on the internet and type in all kinds of things in Google about the first time I learned thermodynamics, or the first time I took it, and then the second time, and the third time, and it usually says something like, the first time I took it, I think I understood about half. The second time I took it, I think I understood about 2/3. The next time I took it, I thought I understood about 3/4. And the next time I took it, I realized I didn't understand anything. Okay. It is not an easy subject. Some of it's easy, some of it's fun, some of it's a game. But some of it is not. Okay. And we're going over the part right now that is not so fun. Okay. It does get better. But don't panic. Don't panic if you don't understand this. But folks, the only way you're going to get this is by reading the book, going online, looking at stuff. This is where you're going to have to actually expend some energy of your own. I'm just trying to help you initiate this process. Okay. Anyway, so don't blank out. If you don't understand something I'm saying, you can either raise your hand or realize that the majority of the class doesn't understand it. Okay. And that we will go over several problems. It's just not to panic, okay? All right. Once again, you have the notes. Whether you want to copy the notes, whether you want to whatever, but these are things. Work is equal to the force times distance. And folks, one of the most important things you're going to learn today is that the units that I expect from you on an exam for work is a joule. Okay? Do not give me liter atmospheres. Don't give me kilograms and newtons. Don't give me anything but joules. Okay? So work is when you got a force on a piston of some sort and then it expands or it goes this way and you have a change in volume. Okay, the distance moved, that's a change in volume. Energy is the capacity of a system to do work. Okay. Work is a transfer of energy to a system and it's equivalent to raising and lowering a weight. We have to have some way to say how much work was done. So the easiest thing that was come up with many, many years ago was, well, would you say we got like a 1 pound weight or a 100 pound weight or something, and 1 joule is equal to being able to lift something this far. Okay? It's a little bit like cars and horsepower. Okay? if you didn't have a metric for how big an engine is, then you wouldn't know whether your well, of course, I guess now we do 5 liter, we do cubic inch now, but there's ways to know whether you got like a powerful engine or not, okay? Same thing here. If you've got X amount of joules, and it's a little bit, folks, like eating food, okay? Here's joules, okay? There's about 4 joules for every calorie. So you get your Snickers bars or something like this, and you look at it, and it's like, okay, this is how much energy is in this Snickers bar, okay? We like to think of calories, okay? But joules is really the work unit. Work on a system is positive. So once again, if I get money, then the sign is positive. If I give out money, if I do the work, then it's negative. And work on the surroundings is negative. That's because if work is done by the system, by me, I'm putting out energy, and therefore the work on the surroundings by the system is negative. Work on a system, so that means if somebody gives me money, I guess I said that backwards. If somebody gives me money, it's positive. If there's work done on me, it's positive. If I do work on something else, it's negative. So internal energy. We're going to have some equations soon, okay? Equations are better. So that the total store of energy in a system is called its internal energy. Problem, folks, is you can't measure that, okay? Internal energy is like everything in your body. All the bonds, all the intermolecular forces, the intramolecular forces, and spin of electrons and everything, okay? It's not easy to do, okay? Maybe it's not even possible. So we don't talk about U. U meaning, you know, the internal energy. We talk about the change. It's a lot easier. It's a lot easier to look at me today and say, okay, Don's internal energy is something. And then I go to Las Vegas or something and I eat a lot of food and I come back and I weigh 4 pounds more. Okay, yes?
What's the difference between internal energy and potential energy?
Okay. So she says, what's the difference between internal energy and potential energy? Internal energy is everything. It's sort of like potential energy is like me sitting on here. I guess potential, there's this much energy stored, okay? But there's a lot more stored in me. Okay, so potential energy is one thing. Okay? I mean, you've got kinetic energy, you've got potential energy, you've got rotational energy, there's all these things. And internal energy is the sum of all of them. But it's not easy to measure. Okay? So, but it's easier to measure the delta. Okay? So we're going to be talking about that. So if a system does 40 joules of work, so the system is doing the work. Don is giving Rafe $40. Okay? So the sign is negative 40 because it's all about me. It's all about the system. If the system does work, then somebody else benefited from it. I didn't. And it's a negative. If instead the surroundings do work on me, then it's a positive. Okay? I've only got about 600 slides that try and show this, so don't panic. Okay, just read this. I'm tired, I've got a sore throat. And you read better than I do anyway. I will note that we're going to talk about the enthalpy later. But that if the delta H is positive, that's endothermic. That means you have to put energy in. Makes sense. Just like with work. Okay? If somebody gives me money, it's seen as a positive. If I do work, then it's a negative. That's called exothermic. And in chemistry, an endothermic reaction is one that requires energy. It requires heat to have it happen. Exothermic is like gasoline burning. Okay? You burn gasoline, gasoline gives off all kinds of energy, and so that's called exothermic. And there's different terms for this in biology. Okay, but it's the same thing. I forget enderogamic and exerogamic or some weird. Anybody know what it is? Okay, well anyway, whatever it is, this is chemistry, so we're going with these. Okay, for process under constant pressure. So we got times, when are we under constant pressure, folks? Constant pressure. This room, if I do a reaction in this room, it's not going to change the pressure. Okay? I always have sort of this one atmosphere sitting on me. So a lot of what we've done in thermodynamics is to say, look, most of what we're talking about is under the constant pressure, because this force, you got to push something against, it's always being pushed against the atmosphere. So that's why we have some special things where under constant pressure, which is what we're usually under, we have some special notations, okay? In that case, the delta H is equal to the change in the internal energy of the system plus the work that the system has done on its surroundings. And that's most of the time. Now, unfortunately, folks, and I'm a little bit lazy, the book uses U as internal energy. That's what I use, okay? The bad news is that, you know, I've complained about not having the book provide me with the lecture in PowerPoint, okay? That's how it's supposed to be, because I'm lazy, okay? They're supposed to give me, all the other books I've ever taught from, gave me 100 slides for a chapter, plus a lot of other stuff. I could get rid of stuff and I could add stuff, but they were sort of like from the beginning of the chapter on. It was in the right order. This book does not. This book just gives a bunch of stuff. There's no necessarily rhyme or reason to it, and they don't even use the same notation as the book. So that's why I'm having to say that delta H, okay, never mind. Okay, they use delta E. That is internal energy. Okay, so that's I guess what I'm trying to say, is that delta E is the same as delta U. Okay? That the notation that we're going to get to when we get to these blue slides that I was provided they're going to use delta E instead of delta U. So here's an example, okay? Look at this right now. So I want everybody to take out your calculator. Let's just do a problem, okay? Just so you're not so scared and intimidated by this. Okay, so look at this problem right here. Here's where we start. There's a certain pressure on us, okay? And here's where we ended up. We pushed, somehow this was motivated to move this piston that far up, from here to here. Okay, here's the change in volume. So first question, did we do work? How do we know we did work? Because it changed volume. Okay, and it was against the pressure. Okay, because work is equal to P dV. Okay, what are two ways? Two ways, folks, to not do work. So one way is, so you got work is equal to negative P dV. Okay, there's the dV. Fine, so that's nice. What would have to happen for there to be no work done in this case? If P was 0. Right? You got two things, folks, you multiply. Pressure times the change in volume. I've already told you if there's no volume change, if you go from here to here, no volume change. V is equal to, delta V is equal to 0. Do we understand that? So there's only one other thing you got to multiply by, right? And that's P. Okay? If P is a real number, then there's work done. What if P is a vacuum? There's no work, because P is equal to 0. V could change by a whole lot, but if there's no vacuum, if there's no pressure, then you got a whole lot times 0. Just like if there's a whole bunch of pressure on this thing, 10 tons of pressure on this thing, and this thing doesn't move. Change in volume is 0. Okay, so there's two ways you can have 0 when actually something looks like it should have worked, okay? So let's just say that this changed by 1 liter, okay? 1 liter. And let's say the pressure on this thing was 1 atmosphere. How much work was done in liter atmospheres? 1. It was 1 liter times 1 atmosphere, you have 1 liter atmospheres. So in my world, folks, my world and Josette's world, because we do gases, we're a gas group, I don't even know what a Pascal is. I mean, I don't know. I honestly could not give you a value for today's Pascal's pressure. Okay? I could give you today's pressure in torr. It's probably about 750, 760 torr atmosphere, in the atmosphere. Or it's about 1,015 millibars. Okay? Or 1 atmosphere. So my world, and we talk about, what do we talk about when we talk about volume? Do we talk about meters cubed? No, we talk about liters, we talk about gallons, okay? And in science, we talk liters because we're all in the metric system, okay? So oftentimes, folks, values of things you're going to be given, the volume changed by 16 liters, and there was 1.2 atmospheres, okay? Not 763,000 pascals, okay? So you got liters and atmospheres, and so liter atmospheres, we need to have a way to convert from that. But for right now, it's okay to say that the work done on this was 1 liter times 1 atmosphere, 1 liter atmosphere. Okay? Pretty soon you'll learn about what the conversion is. But that's how simple it is. Now, if we go from here to here, is work positive or negative? Negative. Okay? For 2 reasons. Okay, and you have to understand, you can be sort of the Big Bang Theory kind of person, where it's all equations, okay, and not a lot of common sense. All right. What I mean by that is, I've told you that work is equal to negative P dV, negative P delta V. Okay. Well, I've got a positive pressure, right? 1 atmosphere. And the delta was a positive value. It got bigger. So 2 positive numbers give you a positive number. And if I've said work is equal to negative that, then that tells you right now that the sign for work is negative. That's the equation part. I also want you to understand and to have a sense for what does this actually mean. If this is done and I give money to somebody, it's a negative. It's a negative cash flow. Okay, this is me. I do something for somebody else and I have less. Okay? So that's why you should be able to look at it and say, okay, this is going to be negative, even without doing the math. If you just like equations, fine. Do that. Okay? I'd kind of like you to do both. To know, okay, this should be a negative value because the volume got bigger. So work is going to be negative. And then you plug it in, work is equal to negative P dV. When I say D, folks, that stands for the delta. Okay, many of you have not had calculus, and that's a calculus term. All right, this is what your book gave me. Yeah, no. So the good news is this is like what this whole section is going to be about. Okay, we're going to break this one down first. And it's just going to be repeating what I said. Okay. I actually added this, believe it or not. I actually modified this slide because before it just said delta is equal to Q plus W. And I put in the delta U is equal to delta E. Okay. Because everything, otherwise, I didn't want to change all of them. So just remember that these two are interchangeable. That this and this are equal to Q plus W. Okay. So any change in the system here has to deal with both heat and work. So if the system gets colder, if it gets colder, then the surroundings get warmer. Okay? And that's a negative Q value. If instead we heat the system up from outside, then that is a positive Q. If work is done on the system, it's a positive. And if work is done by the system on the surroundings, it's a negative. So E is a state function. We have to conserve E. And I've already said that you can't, this is as good as you can do. we're assuming that the whole world doesn't change in energy, okay? That we're in steady state. We can move things around, we can change from mechanical to electrical and nuclear to this and that, but we cannot, E of the universe does not get bigger. Okay, work and energy for gases, okay? And I like gases. Okay. Not sure what we're doing here. These slides confuse me. Okay. So we've got pressure, which is equal to force times area. That's nice to know, but this is what I'm interested in. So we have a pressure, and we got a delta H. Okay, that just means that this height changed from here. This really means a change in volume. Okay, this is the volume right there that changed from here to here. Got this pressure. So if we go from here to here, is that positive work or negative work? Okay, think of the equation. Okay, work is equal to negative P dV. P is positive. You can't have a negative pressure against the law. Okay, that's some law. I don't know what law it is, but you cannot have a negative pressure. You can have a very small pressure, but you cannot have a negative pressure. Okay. And so we've got a pressure which is always positive. So this is what's going to determine whether it's positive work or negative work. If this increases in volume, then that means that delta V is positive. It's a positive times a negative, and negative. Okay? So when this expands, delta V is positive, greater than 0, and therefore this has to be less than 0. Okay. Now it can't, why is there an equal sign here? Because what if this is 0? Okay, so you could have a change in volume and not do any work. Okay, so this is expansion, folks. Once again, there's your equation up there. I will not give you these on the exam. Okay, now look at this one. We got a negative value now for delta V. So now it's a positive times a negative, which is a positive. So that means that the volume got negative, that means work is positive. Work was actually done on the system. See that? Boom, push, this is our system. Somebody gave us money. Now sometimes there's constant volume. Okay? There are things called bomb calorimeters. They're these things that they look like bombs. And they're like this, well, they can be whatever size, but there's very thick steel. You screw the top on and the volume doesn't change at all. So can any work be done in that thing? No. No change in volume. Okay? If something can't move, no change in volume. So, is there any work? No. Constant volume, work. And therefore, the amount of change in energy is equal to the heat. Doesn't mean you can't heat something up. Okay, you can have a reaction in there that's generating heat, but it can't do any work. And so if we look at that, then the delta E is equal to the Q, because there's no W, right? Get rid of the W, because there's no work, and you're just left with delta E equals Q. And from that, folks, what you see here is that delta E is proportional to T. What that means is that the change in energy is proportional to the change in temperature. So if the temperature increases a bit, the E goes up a bit. If the E goes down, then this goes down, or vice versa. So this is an important thing to remember for later. All right. So enthalpy is equal to the energy plus PV. That's a definition. I didn't come up with this. Okay? So delta H is equal to delta E plus PdV. Don't forget though, delta H, or up here, is equal to Q plus W. So, what is the definition of work? Minus PdV. So you got a delta H is equal to Q plus minus PdV plus positive PdV. So delta H, folks, is just equal to the heat. So when we talk about enthalpy, all we're talking about is the energy, the heat given off. Okay? The heat given off is what we're talking about when we're talking about enthalpy. And then once delta H is proportional to the temperature. Okay, do this. An ideal gas expands isothermally against a vacuum. What is Q? You have 30 seconds. So is it smaller than 0, equal to 0, or bigger than 0? That's, you don't have to do a calculation. You just have to look at this and say. Who wants to answer this? Okay, look. Anytime something expands, you got potential for work. Okay? But, this, I realize this is asking for Q, but a vacuum has no pressure. That pressure is equal to 0. So it doesn't matter if this changes or not. Okay, it says it expands. It goes from here to here. It doesn't matter what. Look at it. P is equal to 0. What's 0 times anything? Okay, so 0 times anything is 0. And if we know that Q and W are opposites, okay, if one's 0, what's the other got to be? So let's hope 2 is the answer. All right. So you should have known that because of the little hint I gave you earlier about a vacuum. But once again, it's isothermal. It means that delta E is equal to 0. And then therefore, you just, since delta E is equal to Q plus W, you just say, well then, Q plus W is equal to 0. You move one to the other side, do some algebra. So work is equal to minus Q. How about this one? An ideal gas is isothermally compressed. What is Q? An ideal gas is isothermally compressed. What is Q? So they're opposites, okay? Once again, Q and W are opposites. And so if, in this case, work was done, this is a negative sign. Work ends up with a negative value, okay? I mean, in other words, this is a negative, so negative times a negative is a positive, so we actually gained energy. This is Don getting money, okay? But the price you got to pay for that is because Q is equal to minus W. If this is positive, then what's this? If this is a negative 10, this has to be a 10, right? So Q is actually less than 0 because W was greater than 0. Okay. This is just more of the same. Okay. Adiabatic expansion. So you've got expansions and compressions. Okay, there's two ways you can go. You can either go this way or this way. If it's expanding, folks, I'm doing the work. So the sign of the work is negative because I'm out the money. So there you're going to negative here. And this is a 0 is equal to because we'll get into that in a little bit. Compression, work is being done on me, therefore it's positive. Okay, and this is positive. So here's the question. A gas expands adiabatically against a constant pressure. So I take a spray can and spray it into the room. What happens to the temperature of the gas? So you got three choices. So let me ask you this. Sometimes, folks, so this is like the worst I've seen this class in terms of like fright. Okay? You're all sitting there going, oh my gosh, I don't understand a word this old man is saying. So let me ask you this. Sometimes, folks, you need to help yourself. How many of you have ever held a spray can and sprayed it for a while and noticed there was a temperature change? How many of you have ever, if you spray and it expands, it gets colder, okay? We talked 2 weeks ago about the atmosphere and how air moving up expands and gets colder. That's why we have clouds, okay, and why we have condensation. So you look at this, if you can't solve the problem with the equations that you either think you know or that you've forgotten, think about reality, okay? There may be an equation for calculating how much air is in the tire of my vehicle, okay? But if I show you a picture of the tire being flat and a picture of the tire not being flat, and I ask you which one has more air in it, if you forget the equation, just look at the picture, you know? So look at this. This is expanding. This is going to shoot out of here. It's pushing out, okay? The volume is changing, okay? The volume is changing. So is it doing work? Yes, it's doing work on this, okay? So if it's doing work, the sign of work then is negative, right? Less than 0, okay, because this volume has changed. It's gone from a certain volume to a bigger volume. P's the external pressure, so work is a negative number, okay? Temperature decreases. Folks, I'm sorry that I can't make this any more exciting, okay? It's just, and if anybody out there thinks they can make this more exciting, I would love to sit down for a while and have somebody come up and lecture, okay? Okay. Don't write this down, okay? Listen to me. This is what the book goes through. The work is equal to negative pressure times volume, or times the delta V. We know that. But pressure is usually in pascals, and 1 pascal is equal to this many kilogram, blah, blah, blah. Volume is in meters cubed. Who uses meters cubed? All this. Look in red here, folks. 1 liter atmosphere. Remember 10 minutes ago I asked you a question. You have 1 atmosphere pressure and you expand something 1 liter. How much, I asked you how much work you did. You did 1 liter atmosphere's worth of work. Well, fortunately, somebody has gone through the conversion, all this kind of stuff, and guess what? 1 liter atmosphere is equal to 101.325 joules. Joules is what you report all work in. Do not give me liter atmospheres. Folks, on an exam, if you do not get the exact answer with the exact units right, you cannot get more than half of the points. Give me a 10-point question, you got everything right but the units, you get 5 points. You have to get it right, okay? You'll get partial credit, but do not leave it in liter atmospheres, okay? You must give me the answer in joules. So this is a nice little thing to remember because it won't be given to you. So write that down and imprint it in your brain. Because every question you're given is going to have pressure in either torr or atmospheres, and more than likely in liters, although I could give you meters cubed. How many liters in a meter cubed? What are the dimensions right now? I want to ask this lady right, oops, sorry, lady I just blinded, yeah, you. Oh, you. So, what are the dimensions of a liter? 10 centimeters by 10 centimeters by 10 centimeters. Okay? 10 by 10 by 10. That's how big 1 liter is. Okay? 10 centimeters. How many centimeters in a meter? 100. So how many of these 10 centimeter pieces could I line up next to each other? 10. Okay? So I could put 10 of these 10 by 10 by 10 things together, and I'd have a meter long. But then I got to go 10 this way and 10 this way. So what is 10 times 10 times 10? 1,000. So there's 1,000 liters in a cubic meter. You don't have to write that down. I don't remember that. But you should be able to go, okay, well I do know that 10 by 10 by 10 is 1 liter. Okay? Or write it down. I don't care if you remember that. The point is you can be given volume. I could say the expansion was 2 meters cubed. Okay? Question. 1 atmosphere, the piston moved by 2 cubic meters. How much work was done? You got 30 seconds. 30 seconds. You should be able to do it. 2 cubic meters was the delta V. How much work was done? So how many liter atmospheres? How many liter atmospheres, folks? 1 atmosphere times 2 meters cubed is equal to 2 times 1 times 1,000. There's 1,000 cubic, or there's 1,000 liters in 1 cubic meter. So there's 2,000 liters in 2 cubic meters. Am I the only one awake in this class? So, you've got 2,000 liter atmospheres. How many joules? Multiply by that. 2,000 times this, it's a big number. Okay? A couple 100,000 joules. What's the sign? Negative. There was an expansion. Anytime you have an expansion, folks, work is negative. Because the system did it on the surroundings. Do not forget that 1 liter atmosphere equals 101.325 joules. You maybe don't need to know that quite many significant figures, but you need to know this. So I'm saying you don't need to know all this. What a nice guy I am. Okay, do this right now. Folks, if you're just sitting there not doing this problem, unless you completely understand everything I've said, which I'm not sure I've understood everything I've said, you're losing out. Okay? You need to do these problems. And I guarantee you on Tuesday, there'll be more of this kind of stuff. So come, if you don't have your calculator with you, you don't have a pencil with you, bring something. Okay, who's got an answer? For number 1, how much work is done in the expansion? -60. Perfect. -60 what? Thank you. So yes, we did -60 joules, okay? What is the change in the internal energy of the system? -60, right? Delta U is equal to Q plus W. And that was the work that was done. There we go, look at that, negative PDV. Here's all you got to do. Got to multiply this by this big huge number here, and you come up with -60. Yes?
Well, since there's no Q applied, that means Q equals 0.
No heat is exchanged in the surroundings right here.
So that means that
Q0. Yeah. Okay, now, something that I don't remember ever teaching before is certainly some integral calculus for this level of class, okay? And so we never covered reversible. It was always just PDV, okay, was work. Turns out that there's that equal to or less than sign that I showed you earlier is because of this. That work for a reversible system. Oh, wait, no, I'm on the wrong page here, sorry. Okay. Here we are. So I've already told you that work is equal to negative PDV. And that is for a non-reversible system. Folks, you're going to be told, okay, I will tell you that this is a reversible process or it's not a reversible process. If I say it's not reversible, that means it's irreversible. Okay? I'll try and say irreversible, I may forget. This is the equation if it's reversible. You must know this equation. It will be on the exam. You'll be given R. Okay? And if you notice, this looks an awfully lot like PV equals nRT. Okay? I'm not going to do the math or the derivations to show you why. Okay? Work is equal to minus nRT log. Look at this. What's the difference? Always before, folks, always before we had the delta V. Okay, this is not delta V. This is actually the initial and the finals there, okay? Huge difference, okay? So let's do this problem. We'll do the problem that we did before. Will we do it? Okay. Take out your calculators. Now when I say log, folks, I'm always talking natural logs, okay? The log to the base 10 is nice when we're doing acids and stuff. But when I say log, I was corrected last night on my lecture when I said the log of something. They said, you mean the ln? Oh my gosh. I was having a bad enough day as it was. So the natural log. So let's just do a little experiment. Okay, take your calculators out. Let's just say that the work that we're going to go from so all I'm going to try and do is to have you just tell me the difference between the log, just this part right here, okay? Let's say that the initial volume was 5 liters. Final volume, 10 liters. Okay? Take the log of that. So do that. So this is going to be 10 over 5. Don't forget, your units cancel. You cannot, folks, you cannot put in these two. If I say, let's say I'm being a real mean guy, and I say that the initial volume was 16 centimeters cubed, and the final volume was 0.025 liters. You cannot have a log of units, folks. The units always have to cancel. So I'll try and remember, but it depends on how irritated I am when I write the exam this weekend. Okay? So 10 over 5, 10 liters divided by 5 liters. Liters both cancel. And so now we got 10 over 5. What is the log of 2? Point what? 0.7. Close enough. Okay? Now, so that's 0.7. So that means the amount of work done, and let's say nRT stays the exact same. Okay? So we got a 0.7. Now, folks, go from same delta. Okay? We had a delta of 5, right? We went from 5 to 10. This time let's go from 1 to 6. Volume started off at 1 liter, went to 6. Delta V is still 5 liters. What is the log of 6 over 1? What is it? 1.79. 1.79. What is the ratio of 1.79 to 0.7 or whatever the log of 2 was? It's like about 2.5 or 3, right? What is it? 2.6. So folks, here's the big difference. If you use just delta V, okay, of 5 for those two different situations, you get the same amount of work. If, however, you put in 6 and 1 as opposed to 5 and 10, you get out about 3 times as much work. Okay? So it's very important. If you're given a problem where I just say the change in volume is X, then there's no way you can use this, right? I have to give you the initial and final volumes, okay, for you to even have a chance of using this equation. Anyway, I'll give you R, but that's it. Okay, this is the integral calculus part. This is saying that all the area under this curve here, that is the most amount of energy you can get out, okay? And that's a reversible process. That means you can go easily between these 2 points right here. That's a reversible process. I'll give you whether it's reversible or not. Here's the problem. You got to do this. You got to do it now. So let's just do problem this one. Okay, now don't do this one. Yeah, do this one. Okay, so did you write down the last equation? Who doesn't know what that last equation was? Who doesn't have that written down somewhere? Because you need that equation. Look at this. This is isothermal and reversible. Reversible. So you're going to have to use that equation. Do you remember the equation? Can you remember the equation or can you remember this? I can always go right there. Write that down if you don't have it. Who needs this? Who doesn't need this? Okay, never mind. All right. Here's the information. Solve that one right now. This would be a 6-point, 8-point question on the exam. I'm not sure, probably 6. How many of you have an answer? How many of you don't have a clue? Okay. So you know that equation I put up. You have that equation written down? Do you? Okay. Yes?
How do you incorporate the pressure?
Is there, in that equation for reversible processes, a pressure? Don't need it. You know, you need it for the other one, for the irreversible, but you don't need it for this. Just like you need temperature for this and not temperature for the other. Yes?
Can I say my answer for A?
You want us to give your answer? Yes, what is it?
Negative 2,200.
Yes. So it's negative 2,200 and something. Okay. Now what I want you to do, folks, sometimes I actually want to challenge you to think a little bit. Look at that. Look at that equation. In one case for a non-reversible, all you have is the pressure and the change in volume. Okay? In this case, folks, work is equal to, there's a couple more things involved. Certainly there's a change in volume, although it's the ratio of the change, not the delta. Look at this. Does R change? Never. Okay? In a closed system, does N change? Not in this system. But look at the temperature. What does this tell you? So this guy just said that the answer was 2,200 joules. Okay? Negative 2200 joules. Okay? What would be the amount of work done if this experiment were done at 600 degrees? We are at almost 300. We at 292, right? I doubled that to 600. Double. Not a lot more. Double. Right? Temperature, folks, matters in work that's reversible. So the temperature you're at, instead of saying it's at the North Pole or the South Pole or the tropics, the temperature actually matters when it comes to work for reversible processes. Okay? All right, so the answer is about negative 2200 is what the work was done in the reversible process. Now do the other one. Part B. This would be another 6 points. So I'm going to cheat. Okay? Look at the first part. Read this first part. Path 2 part. In step 1, the gas is cooled at constant volume. How much work can be done at constant volume? So don't be sitting there trying to figure out what the work is. When something, the volume is 0 or the pressure is 0, no work. Okay. So the pressure has fallen to 1.2. So now in the second step, it is heated and allowed to expand against a constant pressure of 1.2 atmospheres until the volume is this. So what is the change in volume? From 8 to 20. So quickly do how much work? What do you got to do? You got to multiply 1.2 atmospheres times 12 liters, because that's the delta V. 8 to 20 is 12. So you've got 12 times 1.2, which is 14.4. 14.4 times 101 is about 1450. Okay, that's a negative. So the amount of work done in this irreversible process is negative about 1500, something like that. Does that make sense? Yes?
If you don't mention that it's reversible.
What? Say it again. Say it loud.
If you don't mention that it's reversible, then we're just supposed to assume that it's not.
I will tell you if it's reversible. Now, if you don't have all the information, if I just say that if in this case, if I had just said the volume change was 12 liters, you can't do the reversible one. Okay, so sometimes that's the clue. If you don't have enough information, you can only do what you can do. I'll try and remember to say it's reversible, irreversible, okay? Okay, next. Did we get that? Folks, do these. I got this out of the book, okay? It's in the book. Read the chapter, okay? So, already did that. So this is the reversible one. Look at this. It's the area under the curve, whoop, like that, okay? So we got all that energy. And you see right here, this is the total of this curve here is 2.2 kilojoules, all right? So the amount of work that was done is 2.2 kilojoules, okay? The amount of heat is 2.2 kilojoules, okay? Because delta U is equal to 0. Now here's the other one, okay? Look at this. We drop with no change in volume. Whoop. No work. We got no work for that, okay? All we got work for was this part, okay? Going from this volume to that volume at this pressure. And it's a whole lot less. Not quite a factor of 2 less. And this is what the picture would show us in terms of that. So a whole lot less energy. This W going out, okay? There's no signs on these right now. This is just showing that work was done here and cooling was done this way. Got to remember this. Note that this is a delta V not actual volumes, okay? So once again, this is not a delta V. You need to have, I have to actually give you folks the temperature. I got to give you N. There's a lot I got to give you. I don't have to give you N, I guess, in order to do the reversible one, okay? And I've never taught reversible before, okay? It's never been in any general chemistry book I've ever taught. It's all just been PDV, so this is a bit of a shock to me. And this just sort of shows graphically, this is the area, this is the 1.2 atmospheres, and here's the volume change. Here's the amount of work that was done, okay? Q is equal to minus W, so once again, work was equal to minus 1.46, therefore Q was equal to plus 1.46. So this is the area. Here's the area we got plus that. We got all of this, folks, because it was reversible. This path was reversible, okay? I don't expect you to be able to explain this on an exam, but I do want you to be able to, if you're given a question like this, to be able to answer it. Okay, I think we should stop. So, folks, just practice. Practice, 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 okay? And, you know, any questions you have, make sure you ask those questions in discussion.